Okay, you can go ahead. Thank you.
Sorry?
You can go ahead now. We're live. Thank you.
Okay, I guess we're good to start. So again, I'll be presenting our speaker today. So Julen, he did his degree in physics here at UAB. Later on, he did his master in astrophysics, technology and high energy physics. Also here at the UAB, we're working with the institute, the ICE. He then did an internship under the direction of Osvaldo Zainelli in the field of astroseismology. He then became a high intro fellow under the direction of Magnus Kua in the field of technology. And he is now doing a short PhD between our institute here, ICE, with Magnus Kua and the Donostia International Physics Center under the direction of Silvia Bono in the field of galactic evolution. And he will be presenting his work. So yeah, go ahead.
Yeah, so hi everyone. As you were saying, I'm working on a short project between the Donostia International Physics Center in San Sebastian and here in the ICE, under the direction of both Dr. Magnus Kua and Silvia Bono. And the project of my thesis is to focus on the search for wandering intermediate black holes in the Milky Way. So before we delve into what is a wandering black hole, let's start by defining what is the intermediate black hole, what we refer for that. So for us, when we say intermediate black holes, we refer as non-stellar black holes with stellar masses between 100 and 1 million solar masses that could possibly be the seeds that at early redshift from which supermassive black holes will be accretion and mergers. They can help us in a variety of fields in astrophysics, from the black hole field directly across the galaxies, the reionization period, tidal disruptions of stars, and even when considering them in intermediate black hole curves in the field of gravitational waves. There's plenty of examples in the literature of supermassive black holes being encountered at redshift 7 and even more recently redshift 11, which implies the existence of even earlier black holes from which these supermassive black holes grew. So now the question is that, are these earlier black holes, these seed black holes, part of the intermediate black hole population that we are detecting at low redshift? And for that, we need to delve into the formation mechanisms of these seed black holes. So seed black holes have a variety of formation mechanisms, such as the merger of two protogalaxies, or the direct collapse of the protogalaxy itself, or the population tree star. And we can differentiate a dichotomy in the evolutionary path of these seed black holes. They can either grow the accretion and mergers to become the supermassive black holes that we encounter at our redshift 7 and even more recently 11, or they can remain with a similar mass and become the leftover seeds, as we call them, that we might encounter at local redshift, at redshift 0. So how do we go from these seed black holes, from these intermediate black holes, to the wanderers, to the wandering black holes that we are trying to locate in the Milky Way? So there's plenty of examples in the literature that predict that infalling of satellites potentially hosting intermediate black holes between 1,000 and 100,000 solar masses may have accreted, may have been absorbed by the Milky Way throughout its formation history. And as a result, a population of wandering black holes, 10 in some cases and 100 in some more optimistic predictions, are expected to wander in the Milky Way halo. And in either case of the number of wandering black holes, other literature predicts that these intermediate black holes, these wanderers, might retain a small cluster of bound stars, a hypercompact cluster, so to say, from which we could detect them observationally in an undirected way. And this is linked to the observational part of my work that I will be showing you afterwards. In any case, such clusters have not yet been detected. So the way we have approached the search for wandering black holes is in two different approaches, computational simulations and with observational data. So I'm going to start by showing you what we've done with the computational simulations, which is the work I did in San Sebastian, and then I switched to the observational data, which is a bit more recent and it will be a bit shorter. So for computational simulations, a brief introduction, we can differentiate three families of simulations. We can go to analytical models, which are a set of mathematical equations very simplistic assumptions is the kind of simulation that you would write in order to model the equations of motions of a double pendulum, let's say. They don't provide details on the structure or the dynamics of the problem, which is not what we're looking for. In the opposite spectrum, in the opposite side of the spectrum, we find n-body simulations, which is the simulation of a large number of particles in a confined box that is precise, but also computationally time expensive. So in the middle of these two worlds, we find semi-analytical models, which is the one that we've used, L-galaxies, that combines both aspects. It has the precision of n-body simulations, but also it's not as time-consuming as them. So I wanted to be clear, in the computational simulations that we've used, we've employed a semi-analytical model, which is called L-galaxies, but L-galaxies is built upon an n-body dark matter-only simulation, which is called Millennium 2. So for the dark matter physics of our simulations, we've relied on Millennium, and for the baryonic physics, we've relied in a semi-analytical model, L-galaxies. So let's start with Millennium 2. What's the part that this simulation is performing? Millennium 2 is a dark matter-only simulation that recreates the high redshift universe. So it starts with filaments of dark matter that, as you go to lower and lower redshift, they start congregating and forming bigger and bigger densities of dark matter. And the way that the code resolves these densities, these overdensities, is with a friend-of-friend group finding algorithm. So whenever the Millennium 2 finds a accumulation of 20 or more dark matter particles, it is considered a dark matter halo. So we went from filaments of dark matter to dark matter halos. And because the dark matter particles have a mass of a few million solar masses, and the minimum allowed mass for a dark matter halo in the simulation is 20 dark matter particles, the halo mass resolution that we're dealing with is of about 100 million solar masses. And this is perfect for the type of project that we're working with, because it recreates the kind of halos that host the kind of galaxies that we might find in the local group, in the dwarf spheroidal parts of the local group, which is exactly the type of satellite dwarf galaxies that may be hosting these seed black holes that we want to follow their evolutionary path. So now we deal with what L-galaxies, the semi-analytical model, does for this project. The L-galaxies at each snapshot make sure that 15% fraction of baryonic mass is filled within each of these dark matter halos. So we go from filaments of dark matter to dark matter halos, and now the dark matter halos are filled with baryonic particles, with baryonic mass. That it takes the shape of a disk type structure, and eventually it takes the shape of a galaxy. And as the dark matter halo gets bigger and bigger, so does the galaxy. So now that we have galaxies inside the dark matter halos, we want to fill them with central black holes. And the way that L-galaxies deals with this is with a black hole seeding prescription, by which every time a dark matter halo is resolved at a redshift higher than 7, there is a certain probability of it being seeded with a central black hole. A central black hole with a random mass chosen between 100 and 10,000 solar masses. And the probability of the seeding taking place relies on both the redshift of the time of formation and the virial mass of the newly resolved halo, which means that as the simulation goes to lower and lower redshifts, it's gonna interpose the kind of dark matter halos that are more and more massive, which mirrors the kind of physics that we might encounter in high redshift universe. So now that we have galaxies with central black holes in them, let's study how we go from there to wandering black holes. And we must distinguish three types of them, three families of wandering black holes: disrupted, pairing, and recurring wandering black holes. So we refer to disrupted wandering black holes, or they start the journey at the center of small satellite galaxies that at a certain point in their lifetimes, they start being accreted and they start getting absorbed by a massive dark matter halo. And in the process, because of the tidal forces exerted over them, these small satellite galaxies get disrupted. And the black holes that once belonged to these small satellite galaxies now start wandering in bound orbits in the more massive dark matter halo. And this is what we call disrupted wandering black holes, because they've undergone a process of disruption. Then we have pairing wandering black holes. Pairing wandering black holes have a similar pathway. But instead of being disrupted by the tidal forces of the larger galaxy, they do not get disrupted, and they manage to reach the larger galaxy, and both central galaxy and satellite galaxy merge with each other. So as a result, the black holes that once belonged to the satellite galaxy now are referred to as periwandering black holes, because they are a few time steps away from becoming a binary system with a central black hole of the larger galaxy. But then we have the final case, which is recoil wandering black holes. Recoil wandering black holes follow the exact same path as periwandering black holes, but we see a few time steps after that. So recoil wandering black holes are the periwandering black holes that are a few time steps away, but then a few mega to giga years pass, and the black holes of the periwandering black holes coalesces with the central black hole of the larger galaxy. And because of conservation of linear momentum, the resulting black hole gets a momentum kick, gets ejected. If the magnitude velocity of this kick is large enough, the recoil wandering black hole starts wandering in a bound orbit, matching the case as disrupted wandering black hole. So we have three different formation scenarios where a central black hole of a galaxy now is considered a wandering black hole. But we do not want to focus on any type of galaxy. We want to focus on characterizing the wandering black holes in Milky Way type galaxies. So we perform a list of constraints on the galaxies that we had in our sample of our galaxies, and then we go from tens of thousands of galaxies to just a few over 100. And now I'm going to share some of the results that we are reaching with this project. So first of all, we expect 10 wandering black holes in a Milky Way type galaxy. We expect that 70% of them to come from a disruption event, 25% to be in the process of forming a binary pair with the central black hole of the larger galaxy, and just 5% to be recoil wandering black holes. We now know that the formation scenario of these wandering black holes, the formation channel by which they become wanderers, might affect their location within the galaxy. So we see that for the case of periwandering black holes, there's a clear population of them within 1 to 10 kiloparsecs, specifically expected at 1 kiloparsec, while recoil and disrupted ones, the secondary population, are at more than 100 kiloparsec. We expect for almost the entirety of the wandering black hole population to have masses of 2,000 solar masses. But in the case of the recoil population, because it has undergone a process of fusion with a larger black hole, this mass has an order of magnitude above. We also study the merger history of the wandering black hole population. So what you're seeing here is the redshift at which the black hole becomes a wanderer in function of the metallicity of the galaxy where the black hole was seated, or better say, where the wandering event takes place. And this is an important distinction because, as you can see, the blue points are much shifted to the right compared to the other two colors. And this is because the recoil, in the case of the recoil population, we are not taking into account the metallicity of the galaxy where the recoil wandering black hole was seated originally, but the metallicity of the galaxy where the recoil event took place. And because that takes place afterwards at a lower redshift than in the other two cases, it is expected to find higher metallicities. We also see, in any case, that up until redshift 5, the formation channels for wandering black holes are dominated by disruption events. And we wanted to focus, if you remember, to the leftover seed population. So the type of black hole seeds that have little to no growth over their evolutionary path, and that have a similar mass to their seeded originally. So we define leftover seeds as those wandering black holes that have not grown more than twice its original size. And when we perform that constraint, we realize that almost 2/3 of our wandering black hole total sample are actually leftover seeds. So now I'm gonna go through some of the same results, but focusing on the leftover seed population. We find that the typical Milky Way galaxy is expected to have 6 leftover seeds. And now, as you can see, we've highlighted the leftover seed population with these diamond shapes. And we find them, of course, the expected masses of these leftover seeds are going to be much lower because we've put a constraint in the mass of this population. But we also see some differences in the location of these leftover seeds in the galaxy. So as you can see, we compare the leftover seed population with a non-leftover seed. So basically, those wandering black holes that have remained with a similar mass from beginning to end, to those wandering black holes that have indeed outgrown more than twice its original size. And when we compare some of the parameters, we see that leftover seeds are encountered 70% closer to the galactic center of a Milky Way type galaxy compared to the non-leftover seeds. And while that is also the case for the recoil population, a 25% more or less, notice that only 5% of wandering black holes are recoiled, so they are so low counts that we usually just combine the recoiled and the disrupted population into just a non-pairing. So basically, we differentiate between the black holes that are very close to the galactic center and those that are very far away. And when we do that, we realize that the difference in location is not so obvious. We also highlight the diamond shapes in the study of the merger history. And we realize that leftover seeds usually undergo a wandering event at a higher redshift than non-leftover seeds, which makes sense because once a black hole undergoes a wandering event, they have less opportunities to grow in mass. So it makes sense that those that have remained with a similar mass have undergone a wandering event at a higher redshift and therefore have had not as much opportunities to grow via accretion and mergers. We also see in terms of metallicity that all of the leftover seeds, we can just fuse these two together, come from galaxies with much more metal-poor environments, which another way of rephrasing that is that galaxies that are more metal-poor do not let their central black holes grow as much as those that are more metal-rich. And we wanted to make sure that all of these results were invariant, or at least that we had a robust model that worked with different black hole seeding prescriptions. So if you remember, there was a certain probability of a galaxy being seeded with a central black hole. And we wanted to make sure that the model was robust enough. So we created two additional models, one in which this probability is doubled, and another one in which the probability is halved. So now we run again all the process from high redshift up to redshift 0. And let's see how it changes the fact that now there should be a higher amount of wandering black holes or a lower amount. And we see that, of course, in the boosted model, compared to the weakened model, there's going to be higher amount of wandering black holes and therefore higher amount of galaxies housed in them. This plot is showing you a distribution of the stellar mass of the galaxy where the black hole is originally seeded. And we are focusing on the disrupted wandering black hole population, which is the most representative one of all of them because it's the most numerous, but this behavior is exactly the same in the other two. And we can see not only that the boosted population has a higher number of wandering black holes, but we also find something that may not be as obvious as the first topic, which is that there seems to be an inverse correlation between the mass of the stellar mass of the galaxy where the black hole is seated and the probability of that galaxy being seeded with a black hole. And if we think about that, it makes sense that because the black hole seeding process takes place at a high redshift, and high redshift is dominated by low mass galaxies, any change in the black hole seeding prescription that we perform at that high redshift is going to affect low mass galaxies the most. So if you shift the initial conditions so that low mass galaxies have more opportunities to host essential black holes within them, you are going to shift the distribution of stellar mass in that case towards more low mass galaxies. And that's why in the weaker model, the expected mass of the typical first galaxy hosting a central black hole is over 1 million solar masses, and in the other case, just about half of it. We also wanted to make some comparisons between our model, between our galaxies, and a hydrodynamic simulation called Romulus 25, which also characterizes some of the parameters of a Milky Way type galaxy in their wandering black holes. So one of the parameters that we wanted to compare is how much percent of the black hole mass budget in a Milky Way type galaxy goes to the central black hole compared to their wanderers. And while in the Romulus 25, this percentage is at the 10% value, we find a much lower 2%. So in our case, in our galaxies, 2% of the total black hole mass budget in a galaxy is focused on the central black hole, compared to the wandering black holes. And the most likely scenario the most likely reason because of these disagreements might be because while Romulus 25 is a hydrodynamic simulation, it has a much lower resolution, which means that while in Romulus 25, the minimum allowed mass for a wandering black hole is 1 million solar masses, in our case, we deal with wandering black holes that are as low as 100 solar masses. So of course, the shifted value of the black hole mass budget is going to be shifted towards a more heavy weight in the wandering population, in their case, compared to us. We also compare with the Romulus 25 simulation the total number of wandering black holes that we might encounter in a Milky Way type galaxy as we go, the cumulative number, as we go farther and farther from the galactic center. And we find a good agreement in the total final number. So in both models, in L galaxies and Romulus 25, it is expected 10 wandering black holes in a Milky Way type galaxy. But in our case, these wandering black holes are much more radially scattered. So these disagreements, so just to put it into numbers, the maximum distance of a wandering black hole in Romulus 25 is about 100 kiloparsec. In our case, the total wandering black hole sample, so including those that are pairing and are very close to the galactic center, 60% of our wandering black hole sample is beyond 100 kiloparsecs to the galactic center. And this disagreement between Romulus and L galaxies might be due to the fact, again, that Romulus 25 has a minimum allowed mass of wandering black holes of 1 million solar masses, which makes them much more efficient in sinking into the center of the galaxy, opposed as our case. So now I'm gonna go through the observational data and some observational things that we've done in this project, and this is gonna be much shorter. But you remember, one way of indirectly detecting this wandering black hole population was through the hypercompact star cluster that theoretically should be orbiting around the intermediate black hole. So what we did was to use two surveys, the Pan-STAR survey and the HSC, the Hyper Super Incam Subaru Telescope survey, in order to try and find these overdensities that theoretically should be focused on the halo of the Milky Way. So we work with the Pan-STAR database, which has a sky coverage with declination between -30 and 90 degrees. And we impose a constraint on the galactic latitude value so that we only take into account stars that are beyond galactic latitude +20 and below -20. So we focus on the North Galactic Halo and South Galactic Halo. With that, we download 150 million stars, and we add another 30 million stars in the case of the HSC, which is, it has much more depth in their GRI bands, but at the cost of a much smaller sky coverage. So we perform a magnitude cut in both of the stars from Pan-STARRS and the stars from HSC, different magnitude cuts, because these magnitude cuts are made in function of the uncertainty values, so that we make sure that the stars that we're dealing with are good quality, let's say, and they are not some artifacts in the middle giving us false positive of overdensities. And from there, we go through a observational process of data reduction, where first we look for overdensities, then we perform a fitting of a color magnitude diagram in order to look for a structure in the main sequence structure in these supposed stellar populations that should exist around the intermediate black holes. And then when possible, we cross-match with Gaia DR3 to look for proper motion space and see if there's some dynamical correlation that confirms the existence of these stellar populations. So we did find three final candidates with Pan-STARRS that you're seeing here. These three candidates were then, well, of course, we built with hundreds of candidates, but these are the final ones. We performed imag versus G minus R and also R minus I color space, this CMD fitting, isochrone fitting, in order to make sure that there was a potential main sequence structure in the stars. We from there derive some distances and some potential age of this stellar population, but as you can see, there are so low number counts that these values of age and distance are quite degenerate. We also, in these three cases, were able to, some of the stars of this stellar population, cross-match them with the Gaia database, which allowed us for a study in their proper motion space. And so we selected only those that had all the stellar components in the stellar population in the hypercompact cluster within a 3 millisecond radius sphere of proper motion space, so that we made sure that it existed some kind of dynamical correlation between all of these stars. And this is a fourth candidate that we obtained with the HSE data. And as in the case of Pan-STARRS, we made sure that both in G-R and R-I, the color values of the stars were aligned more or less as in the isochrone fitting that we wanted to observe. And this is just to put it into an example, the difference between on the right what you see on HSE and on the left what you see on Pan-STARRS. So the candidate that we detected on HSE, just so you can compare the different depths of the two databases, is the one that you are observing on the left on Pan-STARRS. On the left, it wouldn't even be considered as an overdensity, but on the right, you can see a much richer, much higher number of stars that can lend us some information about the potential stellar population. So some takeaway message from this research, from this presentation, is that our results predict 10 wandering black holes of masses of 2,000 solar masses, typically, in a standard Milky Way galaxy at current redshift. We find that the location of these wandering black holes correlate with their formation scenario. So while there's a population concentrated at about 1 kiloparsec from the galactic center, and that comes from past galactic mergers, there's another population placed at more than 100 kiloparsec that has formed as a consequence of ejection due to gravitational ripples, or also in case of the disrupted population that comes from the disruption of satellite galaxies. The differences between that such small and large differences in the distance, in the location of these wandering black holes might explain the absence of strong observational evidence, both from some of the sources of the literature and also from this project itself. As per the leftover seed population, we predict 6 of them in a typical Milky Way galaxy at current redshift. We find pairing wandering black holes that are tagged as leftover seeds to be 70% closer to the galactic center compared to non-leftover seeds. And we find that leftover seeds usually come from more metal-poor galaxies. Again, probably this should be rephrased vice versa, the fact that our metal-poor galaxies, the ones that are not feeding the central black holes enough so that they can grow and therefore not be considered leftover seeds. And we are pretty sure that the results from our analysis are robust against different seeding scenarios, because we are seeing in this characterization exactly what we were supposed to expect from the change on this prescription. And when comparing the computational simulations that we performed with our observational data, we realize that there's a huge part, more than 70% of the total wandering black hole population in a Milky Way type galaxy that is about 180 kiloparsec from the galactic center. And when we compare these to two of the most robust databases that we can find currently, the Pan-STARRS and HSE, in the case of Pan-STARRS, the maximum distance for a proper characterization is about 25 kiloparsec. And in the case of the HSE, we go as deep as 150 kiloparsec, but it only covers 5% of the sky, which is not remotely enough to look for this wandering black hole population. So the good thing is that we found 4 spatial overdensities that show not only a certain structure in their CMDs, but also some kind of dynamical correlation, but they have low number counts, which is the reason why the next step of this research is going to be to analyze these 3 candidates as we've received them from the GTC, from the Osiris telescope in Canary Island. So now we're going to proceed in the following months to analyze these candidates, see if we can correct these low number counts and increase the probabilities of it being stellar populations with dynamical correlation and with internal structure, and therefore confirm the existence of some kind of intermediate black hole candidates in the Milky Way halo. So thanks for listening, and if you have any questions, please.
here.
Wait, so there's this overpopulation, or how you put this, the one that is part of the rate. How do you define what the overpopulation and what I understand is that the random probability that you have
So there's a paper by Green 2021 that explains the exact process in a similar way as we've performed in the search for these overdensities. And they talk about how, theoretically speaking, the best case scenario would be to find 25 stars in a 30 arc second radius environment in the Milky Way halo. Problem is that Milky Way halo is such a low number count density part of region of the galaxy that that kind of population is not reachable. So we find some overdensities that are several sigmas beyond their environment. So this is one of the sanity checks that we performed in order to find for overdensities. Surprisingly, most of the overdensities that we found were false positive, which is not surprising, but they were easily detected as false positives because the CMP diagrams were completely scattered. So it was a complete randomness. It is true that they are low number counts, which is precisely the reason why we are especially interested in analyzing the G versus G minus R magnitude cuts that you've seen, but with the new data from GFTC that we already have. And with that, we expect to pump the numbers from 10 to 15 stars, which is what we are currently dealing with, and to increase them to 20, 25, and then corroborate if they are indeed overdensities or not. And also, finally, the dynamical correlation in proper motion space, which is another yet again another sanity check for these overdensities.
But these are very different, right? So the proper motion was tiny, very small now. What are the errors? So wouldn't you expect that most stars would be anyway around very close to zero proper motion?
Actually, we can go check the exact proper motions of them. So in this case, we've computed that the standard deviation for the proper motion of these stellar populations should be around 100 kilometers per second. If we expect them in the order of 20-30 kiloparsecs from the galactic center. This was performed before some of the results from the computational analysis that we performed. So, for instance, one of the things that we were especially afraid of when dealing with these candidates is that in the CMD diagram, we find them to be at a distance of 50, 60 kiloparsecs, which we initially thought to be extremely far away and completely inadequate. But after dealing with the computational simulations, we now realize that may very well be the case. And the reason that we are just finding low number counts is because we don't have the depth enough to see them. So I don't know, this might be just the stuff that we're seeing, that we're able to see, and overdensities might be confirmed when going to further depth.
There was just wondering, so your results are basically focused on our own Milky Way, a galaxy, and then this black hole that populated with four satellites around it. So you talk about the observations of the black hole at the local universe, Milky Way like galaxies to explore this, to have some statistics and compare.
No, for the moment, the observations that we have planned are just focused on the Milky Way, and specifically because of the position of most telescopes, the North Galactic Halo specifically. In the case of the computational simulation, of course, we dealt with Milky Way type galaxies because we were just working with mock galaxies. But we are not planning, at least for the moment, to work with Milky Way type galaxies at local group or beyond that.
More questions? I actually have one. Right. So when you plot the distance versus the mass of the parent galaxy, like I was wondering if you somehow take into account the mass of the larger galaxy, because I guess like the mass of the larger galaxy will affect if you have like pairing wandering black hole or get like weak hole.
So can you, sorry, are you
Right. So that's on the y-axis you have the mass
of the wandering black hole, yes.
Right. But I was wondering like here you have the distance with respect to the like larger galaxy.
Yes.
Right, but I was wondering like if this distance gets affected by the mass of this larger galaxy. So
no, it should be invariant because we are almost specifically focusing on Milky Way type galaxies. So because we've made some very strict constraints on the stellar mass of the Milky Way galaxy.
Okay, so you don't vary it in mass.
Exactly. There's not such a huge regime of stellar mass of the galaxy, so that we can check. Oh, maybe this is a bias, and what's happening is that we are watching the lower end or the higher end of this specific galaxy.
Thanks. We have plenty of time for more questions. Yep.
You say that the recoil when the black hole is stage that's happen after the baby.
Yes.
Is the disrupted phase another stage for the baby? Is all part the baby disrupted terminal recoil are two stages of the synchronous?
No, and the reason for that is how Millennium-2 stores the data. I mean, in real physics, it could very well be the case. In our specific simulation, it's not, because when a galaxy gets disrupted, the dark matter halo that is hosting it also gets, let's say, it gets eliminated by the simulation. We only consider the higher dark matter halo that is now inside of. So because of that, we have no longer any way to compute the equations of motion of the wandering black hole population that is within that satellite galaxy, and therefore we have no way of tracking it in all its way to the galactic center. So because of that, we just perform a bound orbit physics, let's say, and just consider that they start wandering in bound orbits around the dark matter halo. So they're like two completely different cases, just because the dark matter halo, the subhalo, what we call, gets or not disrupted in the two scenarios. But yeah, in real physics.
Question online.
Oh, well, yeah. Thank you, Julen, for the talk. Are you considering to complement these observations of pansters to radio continuum observations of synchrotron emission to detect compact objects with jets? We do not, but we can talk about it and the benefits that it could have on the research. So here is my email in this last. So maybe we can talk afterwards about it and how it could benefit the research. Because it's something.
More questions? There's some.
Thank you.
I have one last question.
Yeah.
So, you have 4 candidates, right? But also, the region of the Milky Way that you're observing is, it's not a large volume, right? So you have four candidates with small volume, and you're expected to have like potential 10 wandering black holes. Then you would expect that most of these candidates are not really what you're looking for.
So great question. So if we would have only worked with agency, that's completely the case. You're completely on track. The thing is that specifically Panthers has a sky coverage of, I think, 2/3 of the whole sky.
But you have like a magnitude.
Yeah, we have a galactic latitude. So I think the calculus is that we've scoped 30,000 square degrees of sky, which again might be just that it just happens that in that region of the sky we do not find them, but it is what we had to work with. We could extend the search for overdensities also for the galactic plane, the galactic disk, which is something that I've worked a little on. The problem with that is that you, of course, find much more likely such overdensities, and you have quite a problem in trying to distinguish them from just a standard open cluster.
Right.
So, and because the color magnitude diagram and the isochrone fitting, in order to realize the age or theorize the age of the open cluster and distinguish it from the stellar counterpart of very early black hole seeds is quite complicated. So we focus on the halo for that reason, which again, it's another jet constraint of the search. We could extend it to the galactic disk, but it requires some new approach.
Thanks. Okay, if there are no more questions, we can thank the speaker again.
Alba, I stopped recording.
Yeah, I'll stop it. Thank you very much.
I'm going to stop sharing.